Welcome to Lecture 9 of Microeconomic Analysis 1 with me, Dr. Craig Webb. In today's lecture, we are studying one of the great equations of economics, the Slutsky Equation. This is going to formalize our graphical analysis of the Hixian decomposition from the last lecture. That is the idea that the effect of a price change on demand can be broken down into two parts, a substitution effect and an income effect. Let's start with a recap of what we did last time. In Lecture 8, we covered the Hicks decomposition. This decomposed the overall effect of a price change into two distinct effects. The first effect was the substitution effect. This came about because if, for instance, the price of good 1 decreases, then it becomes easier to give up some of good 2 in order to have good 1. That is, the marginal rate of transformation changes. There is therefore an incentive to substitute some of good 2 for more of good 1. Isolating this effect, we hold utility constant and look at the change in demand caused by this change in prices alone, and this is what we call the substitution effect. The second effect was called the income effect, which is the difference between the total change in demand and the change that's caused by the substitution effect. So the total change in demand as a response to a price change is the substitution effect plus the income effect. The income effect arises because, in a very real sense, the consumer becomes richer when the price of one good decreases, holding everything else constant. They are richer in the sense that they can afford bundles which they couldn't previously afford. After a price reduction, they're able to get onto a higher indifference curve and enjoy a higher level of utility. So this is what we mean by the income effect. After we factor out the substitution effect, which is motivated by the fact that the price ratio changes, then the remaining part of the total effect is the income effect. If a consumer has indifference curves which are strictly convex, then the substitution effect is always negatively related to the price change. Strictly convex means that the marginal rate of substitution is diminishing, which is a very common and useful assumption in microeconomics. The fact that the substitution effect is always negatively related to the price change means that the substitution effect is moving in the same direction as we might expect to be in accordance with the law of demand. If a consumer's demand violates the law of demand, it is not because of the substitution effect. The income effect has varying directions depending on whether the good is a normal or an inferior good. We analysed some of the results of Hixian analysis last time, and we saw that normal goods must obey the law of demand. It is impossible to violate the law of demand when a consumer has strictly convex indifference curves and considers that good to be a normal good. Normal good means that changes in demand are positively related to changes in income. For inferior goods, it's a little more subtle. The income effect counteracts or moves in a different direction to the substitution effect. Now, if this income effect only partially counteracts the substitution effect, then overall the consumer will demand more of a good after a price reduction. That is, they will satisfy the law of demand. If the income effect is very strong, and so strong that it dominates the substitution effect, then it's quite possible for a consumer to violate the law of demand and demand less of a good even though its price has reduced. In the last lecture, we learned all these facts using graphical techniques. Today, we'll be looking at the Slutsky Equation, which formalizes this analysis and we'll prove the basic result that total change can be decomposed into a substitution effect and an income effect, but we will prove it today using calculus methods. Our first step to understanding and deriving the Slutsky equation will be to study what is called the expenditure minimization problem. Recall the consumer's problem, which is essentially find the best way of spending a given level of income. So the ingredients for that problem were the consumer is given the prices of each good, unit prices, and they are given a level of income, and they have to choose their most preferred bundle of goods. So they need to find the best way of spending a given level of income. The expenditure minimization problem is essentially a dual of the consumer's problem. Rather than having a given level of income and trying to maximize utility, the expenditure minimization turns the problem upside down and asks the question, find the cheapest way of achieving a given level of utility. So the ingredients for this problem for a consumer will be the prices for each good, they will be given the prices, and they will be given a target level of utility. Then they have to find the bundle which minimizes the expenditure required to achieve that level of utility. So formally, the expenditure minimization problem is the following. We have to minimize by choosing Q1 and Q2, the expenditure required for that bundle, which will denote capital E, which is equal to expenditure on good 1, P1 times Q1, plus expenditure on good 2, P2 times Q2, subject to a constraint which says the utility of this bundle that we are choosing has to be equal to a target level of utility, and we'll call this target level of utility U bar, so capital U with a line on top of it. When we see a constrained optimization problem like this, we already know several methods for solving it. For instance, the Lagrangian would be this for this problem. You would take the thing that we're trying to minimize, P1 times Q1 plus P2 times Q2, and then deduct from that the Lagrange multiplier lambda minus the difference between the target utility U bar and the utility level of the bundle that contains Q1 units of good 1 and Q2 units of good 2. Taking this Lagrangian and partially differentiating with respect to Q1, partially differentiating with respect to Q2, and then partially differentiating with respect to the Lagrange multiplier lambda, this gives us three equations, and if we find the Q1 star, Q2 star, and lambda star that simultaneously makes these equations equal to 0, then this is the first order condition for solving this problem. As well as using calculus, we've also developed graphical tools for solving constrained optimization problems. So this diagram just recaps the utility maximization problem, maximize utility subject to the constraint that the bundle is affordable, so lies on that budget line. Let's now look at the expenditure minimization problem using a graphical approach. So let's have a look graphically at what the expenditure minimization problem looks like. Now, just to recall, the expenditure minimization problem is this: minimize by choosing an amount of Q1 and an amount of Q2, the expenditure required to purchase the bundle Q1 and Q2. So P1 is given, the price of good 1, and P2, the price of good 2, is given to us. The expenditure required to purchase that bundle is P1 times Q1 plus P2 times Q2. So we want to minimize this expenditure. Now clearly, if there was no constraint, you would solve the problem by buying 0 of both. But there's a constraint that says when you choose this bundle, Q1 and Q2, the utility of that bundle has to equal a target level of utility, which we're going to denote U bar. So U with a line on top. So how do we represent this? Well, first of all, let's represent the constraint. I know that bundles of goods that have the same level of utility, graphically, that means they all lie on the same indifference curve. So I could draw a downward sloping convex indifference curve and then label it and say, well, the utility of every bundle of these two goods along this indifference curve all have the same level of utility equal to the target level of utility U bar. What about this, the thing we're trying to minimize here? Well, let's just, if I quickly write P1 times Q1 plus P2 times Q2. If I look at all bundles that cost the same amount, okay, so if I pick a particular amount C, so just a constant, what does this look like? If I rearrange, I will get Q2 equals C divided by P2 minus P1 over P2 multiplied by Q1. So so if I look at a set of bundles that require the same level expenditure, they just lie on a straight line. Of course, if this is equal to Y, the consumer's income, then this is the equation for the budget line. But we're not going to take Y as the given in this problem. We're going to take a target level of utility and ask what level of income do we need. Now, if I want to represent these, I know the slope is minus P1 over P2. So for instance, if I draw a straight line like this and say that this has slope minus P1 over P2, then I know that every bundle along this line requires exactly the same level of expenditure. Of course, none of these will be solutions to minimizing our expenditure because subject to this constraint, because here every one of these bundles seems to be on a higher indifference curve than the target level. Okay, so if I want to solve this problem, it's going to be characterized by a tangency condition. I'm effectively trying to get on the lowest of these downward sloping straight lines. So I'll jump right to it. We should be fairly used to tangency conditions by this stage. So the solution to this problem occurs at a tangency that looks like this. So it would be a particular point here where the marginal rate of transformation, the slope of these expenditure lines, is precisely equal to the slope of the indifference curve. This shouldn't be surprising because first order conditions for maximization problems and for minimization problems look the same. So I'll just make a note that one of the first order conditions is marginal rate of substitution equals marginal rate of transformation. So that would be the first equation that characterizes the solution. And of course, the second equation would be that the utility of this particular bundle is precisely equal to the target level. So these two equations would characterize the interior solutions to expenditure minimization problems. Okay, so we went through that rather quick, but it's just building on what we already know. I could denote this amount here as Q1 star, and this amount here as Q2 star. Okay, now we give these specific names. We call Q1 star is called the Hixian after John Hicks, so Hixian demand. Okay, so the solutions to the expenditure minimization problems are called Hixian demands. We'll talk more about these and we'll see why that's an appropriate name. So similar how we have derived demand functions, we could think of this Q1 star as being a function, let's call that H1. And what are the inputs for this function? What does Q1 depend on? Well, we were given the prices of both goods, so P1 and P2. We weren't given a level of income, however, we were given a target level of utility, U bar. This is called a Hixian demand function. It's also called a compensated demand function. Okay, so and the demand functions that we've seen before, so for instance when we had a function D1 which was a function of P1, P2 and income Y, this is often called an uncompensated demand function, or it's sometimes called a Marshallian after the economist Marshall. So sometimes the demand that we've seen so far is called Marshallian demand, and this Q1 star as a function of P1, P2, and the target level of utility U bar is called the Hixian demand, or sometimes called the compensated demand function. You can see the sense in which it's compensated in a minute, but it's because this only captures the substitution effect. So there's no income effects going on here because we're fixing a target level of utility. So in a sense, we're compensating, we're changing the consumer's income in each for each price level in order to fix utility at a given level. So we could construct this Hixian demand function in a very similar way to which we drew the Marshallian demand function. If we remember to draw Marshallian demand, we drew a diagram that showed price changes, and then underneath we produced a diagram which captured the Marshallian demand function. So let's do that now. We'll derive graphically the Hixian demand function with price on the vertical axis and quantity demanded on the horizontal axis. So let's derive Hixian compensated demand graphically. So to do this, I've prepared two diagrams. So in the first diagram on top, I've got the amount of good 1 on the horizontal axis and the amount of good 2 on the vertical axis. So this is a commodity space diagram. Below, I've drawn good 1 on the horizontal axis and price on the vertical axis. So this is the usual diagram in which we draw demand functions, or what we should now call Marshallian demand or uncompensated demand. When economists say demand functions, they typically mean Marshallian demand or uncompensated demand, as we've already seen so far. So let's start by just recapping very quickly the construction of uncompensated Marshallian demand. So we begin with a prices P1, P2, and income Y, and we construct a budget line like this, and then we observe the consumer choose some bundle of goods, let's label that E, okay, which is characterized by that tangency condition, and all income is spent. So the tangency condition is the slope of the indifference curve is equal to the slope of the budget line, and they spend all of their income. So this amount here, Q1, was the Marshallian demand, uncompensated demand for good 1 when the price is P1, the price of good 2 is P2, and income is Y. So let's draw this point down here. So let's label P1 here, trace this down, Q1. And so we get a point like this, okay? So this tells us when the price is P1, demand is Q1, uncompensated demand is Q1. So we've seen that before. and we're reading the kind of diagram sideways, as is conventional. Now suppose we have a price reduction, so let's let P1 prime be less than P1. So if the price of good 1 goes down, we know how to represent this graphically. This intercept on the vertical axis doesn't change, because that's the point at which, if I spend all my income on good 2, how many units could I get? That stays the same. But the budget line pivots outwards and gets flatter. So connecting these 2 points gives me the new budget line with the new marginal rate of transformation using this P1 prime as the price of good 1. Okay, and then if, for instance, we saw the consumer choose this bundle here, let's label that E prime, then Q1 prime is their new demand, or their uncompensated demand for good 1. Let's trace that down, Q1 prime here. When the price fell, so let's just draw P1 prime below P1. And so when we connected these 2 lines, drawing something like this is how we constructed the Marshallian uncompensated demand function graphically. Okay, so that's all what we've seen before. Okay, so where does the Hixian demand come into this? So remember that for Hicks, Q1, H1 is a function of the price of good 1, the price of good 2, and a target level of utility U bar. Okay, so let's take this target level of utility here. So let's say that this indifference curve satisfies the utility of Q1, Q2 is equal to our target. Okay, then hopefully we can see that, well, if at the initial price level, the Hixian demand, so I would be minimizing the expenditure required to get this level of utility when the price is P1 and P2. So I would effectively be, if I just kind of hold this ruler up, I'd be looking at straight lines with the same slope and reducing my expenditure until I just have enough to achieve this level of utility. And this, of course, happens at the same point. Okay, so at this point, Q1, this is also part of my Hixian demand function for those 2 price levels and that target level of utility. So what about if the price changes to P1 prime? Okay, so if the price changes to P1 prime, then there is a new slope. It's this, the new slope is minus P1 prime over P2, okay, which is the slope of the new budget line. Now, this new bundle E prime has higher utility than U bar. So for the Hicks demand, what I'm looking for is trying to, once I know that this is the new price ratio, I want to get onto this indifference curve where utility is equal to U bar in the cheapest way. So I'm effectively taking this line and tracing it back until I just have a tangency here. Okay, so something like this. Now that should feel very familiar. Let's call that E double prime, because going from Q1 to Q1 double prime, we've already given that a name. That is the substitution effect, is the substitution effect. And this is precisely what the Hixian demand function is capturing. Okay, it's a demand function that factors out the income effect, and which it compensates for the income effect, in a sense, is why we call it compensated demand, and only includes the substitution effect. So if I trace this point down, Q1 double prime, when the price is P1, I get a point here, and connecting these with a line, okay, I get a different curve. So this curve here is my Hixian demand for good 1, when the price is changing, the price of good 1 is changing in this diagram. I'm taking the price P2 as fixed, and I'm taking the target level of utility as fixed. Okay, and I've got that target level of utility in this example by taking the level of utility the consumer achieved initially when they had this level of income. Okay, but I could have chosen a different target level of utility, which would correspond to a shift in the Hixian demand function. You can see here that the Hixian demand function is steeper than the Marshallian demand function. Okay, so it's Q1 to Q1 double prime is a smaller jump than Q1 to Q1 prime. Okay, the reason this happened is because I've drawn a picture of a normal good. Had I drawn a picture of an inferior good, where, for instance, E prime were over here, if I had done this example, then the Marshallian demand would have been steeper than the Hixian demand. We will talk more about that in the next lecture. Finally, we should notice that because the Hixian demand is only capturing the substitution effect, if I assume strictly convex indifference curves, then I immediately know that that the Hixian demand function always satisfies the law of demand. Okay, so this partial derivative of the Hixian demand function with respect to price is always negative because it's only capturing the substitution effect, and that always works in the same direction as the law of demand. Okay, so you would always want to substitute in favor of the cheaper goods once you compensate for income effects, once you remove income effects from the equations. Finally, let's just quickly mention that this is, because we will see this in the Slotsky equation, that I could write the partial derivative of this Hixian demand function for good 1 with respect to the price of good 1, taking everything else as constant. If I multiply this by P and then divide it by Q1, then this, of course, is the elasticity, which we're going to denote epsilon star. Okay, so the elasticity of Marshallian demand, okay, we denoted epsilon, and we're going to denote the elasticity of the Hixian demand function as epsilon star. So we'll see that at the end of the lecture. So now that we've derived Hixian compensated demand functions from the expenditure minimization problem, let's talk about what's called the expenditure function and a famous result in microeconomics called Shepard's lemma. A lemma is essentially a small theorem. So it's a result that's often used to prove other theorems mathematicians call a lemma. So let's recall the expenditure minimization problem, which is to minimize by choosing Q1 and Q2 the expenditure P1 times Q1 plus P2 times Q2. So minimize by choosing these amounts, the expenditure required in order to, so subject to, in order to achieve a target level of utility. So the utility of Q1 and Q2 is equal to some target level of utility U bar. Okay? Now, when we solve this problem, we get a Q1 star and a Q2 star, and we called these the Hixian compensated demands for good 1 and good 2. Okay, now we could write these as in terms of Hixian demand functions. So the Hixian demand function H1 for good 1 depends on the prices of both goods and depends on that target level of utility. Q2, we could write the Hixian compensated demand function for this, which tells us, which is a function of the price of good 1, the price of good 2, and the target level of utility. So Hixian demands are telling us essentially the amount of good 1 that you would purchase when the prices are P1 and P2 and you're targeting a level of utility U bar. You're choosing a bundle that minimizes the expenditure required to get this level of utility, and these amounts, Q1 star and Q2 star, are effectively the amounts that solve the expenditure minimization problem. Okay, now this doesn't tell us the actual level of expenditure. If I go back to my diagram with the expenditure minimization problem, we could see how to read this off. So let me, if we recall this diagram where I had my expenditure minimization problem, I could look at this axis here and say, well, how much am I spending along this line? And I could read it off here. It would be P1 times Q1 star plus P2 times Q2 star. And because I'm intersecting the axis, that would be divided by P1. So this, the top would be some level E divided by P1. So once I know this point here, I can read off the amount of expenditure required for every bundle along this line, knowing that the solution to the expenditure minimization problem lies on that line. Okay, so we give this a name, we call it the expenditure function. So if I write the expenditure as a function of P1, P2, and the target level of utility U, it's effectively telling me what's the smallest amount of money that I need, not units of goods. What's the smallest amount of money that I need in order to achieve the target level of utility U bar when the prices are P1 and P2? Okay, so we can jump straight to this and say, well, this is P1 multiplied by our Q1 star plus P2 multiplied by Q2 star. That gives the expenditure required to purchase the bundle Q1 star, Q2 star, which solved the expenditure minimization problem. Okay, so this is called the expenditure function. Now, it's a function of target level of utility. It might not be immediately obvious here, but I could write this as equal to P1 and then note that Q1 star is the Hicks demand function, Hicks demand for that good when the prices are P1, P2, and the target level of utility is U bar. Okay, so I've just replaced Q1 star with an expression that clearly depends on this target level of utility, plus P2 times H2, P1, P2, and depends on target level of utility. So this is the expenditure function. We can see it depends on the ingredients of the expenditure minimization problem, the two prices, and the target level of utility. Now, how could I then, well, for instance, we could ask the question, if I knew the expenditure function, okay, so if this was the thing I started with, the expenditure function, how could I get the Hixian demands? Okay, well, and it's a very simple result. If I differentiate the expenditure function, partially differentiate with respect to the price of good 1, what happens here? I've got the price of good 1 being multiplied by this term here, which is the Hixian demand function for good 1. Okay? And if I partially differentiate the expenditure function with respect to the price of good 2, I get this very similar result that outpops the Hixian demand function for good 2. Okay? So this result, the fact that if you partially differentiate the expenditure function with respect to a good's own price, that is a fact that is known as Shepard's lemma. Okay? And again, lemma just means a small theorem or a result that is used in a sense as a building block of another theorem is what mathematicians call a lemma. So Shepard's lemma is a very important foundational result in consumer theory. We're going to use this next as we derive the Slutsky equation. So now we have everything we need to derive the Slutsky equation. So let's suppose that a consumer solves a utility maximization problem, so we are in a utility maximization problem. What happens? We're given a price of good 1, we're given a price of good 2, and the consumer is given income Y. And suppose that the consumer solves this problem choosing, let's say, a bundle Q1, Q2. And let's suppose that the utility of Q1 and Q2 is equal to U with a bar on top, so U bar. Okay? So the consumer faces a utility maximization problem, find the most preferred bundle of goods, given prices P1 and P2, and given income Y, so we have to choose an affordable bundle of goods. They solve this problem by choosing this bundle Q1, Q2, and it just so happens that the utility of that bundle, let's just denote that U bar. Okay, so nothing major so far. Now, this next line, I think, is one of the hardest lines of equations in the entire course. Firstly, conceptually, it's difficult. We're going to think about our definitions in multiple ways at the same time. And secondly, we're bringing lots of things together all at once. So really make sure that you understand this line of equations here. Okay, so given what I've said, let's go through this. Q1, well, we've also called the amount Q1 that solves the utility maximization problem, we call that the Marshallian or uncompensated, or simply the demand for good 1. Okay, so if D1 is the demand function and we plug in P1, we plug in P2, and we plug in income Y, Q1, the thing that solves this problem, is what should pop out. Okay. Now also, because this is characterized by a tangency condition, and we've seen this already in the lecture, that if my target level of utility was U bar, okay, so if I was doing an expenditure minimization problem and I faced prices P1 and P2, and I had to try and achieve this level of utility, well, this level of income would be exactly what I needed, okay? In other words, this is precisely the Hixian compensated demand when the prices are P1 and P2, and the utility level, the target level, is precisely the amount of utility I could achieve when my income is Y, given these prices. Okay, so we've seen that already when we constructed Hicks demand graphically. So just make sure we're solid with this first step. Okay. Now the second thing I want to write here is that this is also equal to, here, this target level of utility, income Y is just enough to achieve this. So I could write that similarly by saying, well, this is the demand for good 1 when the prices are P1 and P2. And how much income do I have? Well, I have Y, and that's just enough income to achieve this level of utility. How could we write that? I could say the expenditure function evaluated at this target level of utility this amount here is telling me the smallest amount of income I need when the prices are P1 and P2 to reach a target level of utility U bar. And I already know that that's precisely equal to the consumer's income given the definitions that I've used above. Okay, so that's a very difficult line. I've almost gone off the page. It's a very difficult line, and we really need to be solid with that. So go over that and ask lots of questions. Okay, now we've got this. We've got the, if I just write it more neatly, H1, P1, P2 target utility is equal to Marshallian demand when I have just enough income to achieve that target level of utility. Okay, now I've got this equation, a deep equation that requires kind of lots of study of the definitions and going over the graphs to really grasp. But now I've got this, now I can go through the motions of applying some calculus to this. So I'm going to treat this as an identity and say, well, if I'm changing any of these things, the target level of utility, if I change it over here as well, this will remain the same. If I'm changing the prices P1 and P2, apologies. And I can treat this as an identity and differentiate both sides. Okay, so let's differentiate Hicks demand with respect to price of good 1. And let's do the same over here. Now here I've got the price of good 1 appears here and appears here. So I'm going to have to do each in turn. So if I differentiate partially this demand with respect to good 1, the price of good 1, and then the price of good 1 is also going to affect this expenditure function term. So I'm going to add the, I'm going to partially differentiate demand with respect to expenditure, and then differentiate expenditure partially with respect to the price of good 1. Okay, so that's just taking the partial derivative of both sides with respect to P1. Okay, now if we remember Shepard's lemma, it said that if you differentiate the expenditure function with respect to a good's price, out pops the Hicks demand. Okay, which I know is equal to Q1. So I could replace this term here with using Shepard's lemma. So the partial derivative of the Hixian demand with respect to the price of good 1 is equal to the partial derivative of the Marshallian demand. Let's put D1 here, sorry. Of Marshallian demand for good 1 plus the partial derivative of Marshallian demand with respect to expenditure or income multiplied by Q1. At this point, we've essentially derived what I would call the Slutsky equation. However, the book goes a little further and does some cleaning up. So let's go on the slides and do that now. So if we take the expression we've found so far, the partial derivative of Hixian compensated demand with respect to own price being equal to the partial derivative of Marshallian demand with respect to own price plus the partial derivative of Marshallian demand with respect to expenditure or income multiplied by Q1. Now we're going to multiply each of these terms by P1 over Q1. So as you can see, we're going to be deriving an expression involving elasticities, and that's why we're doing this. And then this final term, this derivative of demand with respect to expenditure, we're also going to multiply that by E and divide it by E. So if you compare this equation in the middle of the slide to the equation above, you'll see that I've just multiplied every expression by the same thing, P1 over Q1, and multiplied the final expression on the right by 1, which is expenditure divided by expenditure. Now, if I do this, I can see clearly that on the left-hand side we have the elasticity of compensated demand, something we denoted epsilon star, and this is equal to the elasticity of price elasticity of demand in the normal sense, the elasticity of Marshallian uncompensated demand, which we denoted epsilon. And then we have this term at the end, plus P1 times Q1 divided by expenditure, multiplied by this this thing that looks like an elasticity. So let's examine these terms. The first of these, P1 times Q1 over expenditure, well, this is, we've seen this before, we labelled it theta, and it's the fraction of income that we spend on good one. Okay, so what proportion of our income do we spend on good one is theta in this case. And the second term is what we called psi, which is the elasticity of demand with respect to income. Okay, so let's replace them terms, and then we get that epsilon star, the elasticity of compensated demand, is equal to epsilon, the price elasticity of demand, plus a weighted income elasticity, where the weight is this proportion of income spent on good one, and income elasticity is defined in the normal sense. If we rearrange this term, this expression in the middle, we get that elasticity of demand is equal to elasticity of compensated demand, so the elasticity of Hixian demand, minus a weighted income elasticity. This process of cleaning up our equations at the end has left us with a very elegant way of expressing the Slutsky equation as demand elasticity being equal to Hixian elasticity, elasticity of compensated demand, minus a weighted income elasticity. So now we've derived the famous Slutsky equation, which says that the price elasticity of demand, the responsiveness of demand to price changes, is equal to the elasticity of Hixian demand or compensated demand minus a weighted income elasticity. Okay, so if we examine this equation, equations don't get much more beautiful in economics than this. Well, what do we know about each of these terms? Hixian elasticity, for example, is always negative because for convex indifference curves, the substitution effect is always negatively related to the price change. So Hixian demand ignores whether a good is normal or whether a good is inferior. It compensates for income effects. It captures pure substitution effect, so Hixian elasticity is always negative. When it comes to weighted income elasticity, well, this can go one of two ways. For normal goods, this is a positive number, so we're taking a negative number and deducting a positive. So we end up ultimately with demand elasticity being negative. For inferior goods, weighted income elasticity will be a negative number. So we're deducting a negative number. That is, we're adding something. So demand elasticity in that case for inferior goods, it could be negative, but it could also be positive, distinguishing between the inferior non-Giffen and the inferior Giffen goods. Ultimately, when you look at this equation, you should simply notice that it's doing the same thing as the Hicks decomposition. Demand elasticity, what is the total responsiveness of demand with respect to a price change, has been broken down into the Hixian elasticity, which captures only the substitution effect, and then adding to that is what we call an income effect, which here is the weighted income elasticity. Don't worry that I've changed the minus sign to a plus. I'm simply saying that the total effect is the substitution effect and the income effect. Okay, so the Slutsky equation, this beautiful equation at the top of the slide here, captures precisely Hicks's analysis that the total effect of a price change is equal to the substitution effect plus the income effect. So there we have it, Slutsky's famous equation for decomposing the total effect of a price change into the substitution and income effects. This was not an easy lecture, so hopefully it at least motivates you to go over previous material to make sure we're completely solid with our understanding of everything, so that we fully understand the derivation of Slutsky's equation. In this respect, please ask lots of questions. I'm always here and happy to talk about economics with you. In the next lecture, we'll be continuing our work on consumer theory, our final pass, where we'll be looking at issues of consumer welfare. How do we measure consumer welfare? For instance, what effect on consumer welfare is there when the price of a good goes up, or when the price of a good goes down? How can we measure this? We're going to look at 3 different ways of measuring this, which is going to be based on the ideas mainly developed in the last 2 lectures. Very exciting stuff. I look forward to seeing you next time. In the meantime, take care.